Lecture 2.1, Overview of the First Law. With our inclusion of heating into the work energy theorem, the first law states that working plus heating equals the change in internal energy. So what do we really mean by the word change in internal energy? In this course, we talk about the change of internal energy of atoms / molecules. But also internal to an object is the internal energy of the nucleus. And if you get even subparticles, you also have the energy of particles. So that's really what we mean by internal, but we're not interested in what happens at the nucleus. That's a factor of essentially 10 million difference. And we're not interested in elementary particles. And, who knows what else. But when we talk about this is what I mean by this change in the micro. So this begs the following question. Why should we care about the internal energy, which is the kinetic energy of some atomic or molecular, particle, if the energy of a single atom is surely tiny? Why should we care? Here's a rough estimate. Between Kmicro of an object versus Kmicro. So let's start with the macro kinetic energy of an object. And in this object, what we're going to do here is that we're going to slide an iron block. And what I mean by this here, I'm going to give it some mass, some arbitrary mass. So that's 500 grams. That's about a pound. Across a frictionless floor. So picture-wise, I imagine that I have a block right here. And according to the work energy theorem, I can only talk about changes. So let's say that this is my block right here. And then what I'm going to do here is that now I'm going to do work on this block. And what I'm going to do here is that I'm going to change its kinetic energy. And just for the sake of numbers here, I'm going to say that the final speed of this block over some distance is going to be 20 meters per second. And that turns out to be about 50 miles an hour. So this block is moving pretty quickly. We can clearly tell us then, so if I look at the macro energy of this thing, that means the change in the macro, there is no change in potential energy. So therefore, all of the work goes into changing the macrokinetic energy, which is in 1/2 mv squared minus 0. And if you plug in the numbers, you get 100 joules. and that's going to be your work done or the change in kinetic energy of the block. And that's a fairly standard type of thing to look at. Now, in our case, there are microkinetic energies within the block. And this is what we want to calculate. So clearly, right, there are numerous iron atoms in the block. And the way we have to calculate the total kinetic energy within the block is that I need the number of iron atoms times the kinetic energy of a single iron atom. So you could see that I really got to calculate two things here. I need to calculate the number, and I need to calculate the individual kinetic energy of these guys here. So let's go do that. So the first thing I'll start off with is the number N of iron. And what we do here is that we have to go back to chapter 1. So from the definition of a mole, here's what we have. The mole number is really the mass of the sample, which is something that we have, that's 500 grams. And then we need the molar mass of iron. So if I come in and I paste this, you could see that I have the molar mass right here of iron, which I'm going to approximate to 56 grams per mole. But it's also equal to the number in that sample divided by Avogadro's number. So what I'm going to do here is that I'm going to solve for N iron here. And as I do that, you can see here is that N iron is then going to be the mass of the sample divided by the molar mass times Avogadro's number. So if I start putting in my numbers here, you could see here is that the first number is going to be the mass sample, and then the molar mass is 56 grams per mole. And then Avogadro's number is 6.022 times 10 to the 23, but that's atoms per mole. So if I compute this number, I get that this number is 54 times 10 to the 24 atoms. So now this is closer to 10 to the 25 than 10 to the 24. So I'm going to say that this is 10 to the 25 atoms, iron atoms, in this block of iron. So now the next thing that I got to do here is that I need to calculate the microkinetic energy here. So now what I'm going to do here, I need the the kinetic energy of a single iron atom, which should be 1/2 the mass of an iron atom times its speed squared. Well, here's what we know here. When I look at the element of iron, note that it says that its molar mass is 56. So what I'm going to focus on here is I'm going to focus on the mass of an iron atom first. So when you look at this thing, this is what we see here. The mass of an iron atom, well, it's composed of its nucleus and, of course, its electrons. Now, what you're finding here is it turns out that if I look at the nucleus of iron, you're going to see that there are, on average, 56 neutrons and protons. So when I look at this thing, this tells me that there's 56 protons and neutrons inside the nucleus. Now, when I look at the mass of the electron, it turns out that one proton or one neutron is 1,800 times larger than the mass of the electrons, so I'm going to ignore them. So here's a fact, that the mass of the proton is effectively the mass of the neutron. The neutron is just a slightly larger value, but not by much. So this tells me then if I want the mass, I can approximate this by 56 mass values of a proton. And then if I look up the mass of a proton, it's 1.67 times 10 to the minus 27 kilograms. So if I look at this thing, this is going to be, so 56 times that, that's going to be roughly about closer to 100. So I'm going to say that this is approximately 10 to the minus 25 kilograms for the mass of an iron atom. So now I have the mass. And then the next thing that we need, if you just kind of Google this, we could say that at room temperature, iron atoms roughly move at V equal to 500 meters per second. So now I can compute my kinetic energy of the iron atom. So here I go. So the kinetic energy, actually, we're going to have to compute two kinetic energy terms. Okay, so how about if I write that? So now we want to compute two kinetic energy terms. What we just highlighted is we wanted to say, yep, the kinetic energy of an iron atom was then going to be 1/2 the mass of an iron atom times its velocity squared. Now remember, we have to speed up the iron. Like, kinetic energy by itself is meaningless. You know what? I'm going to do this correctly. It's the change in kinetic energy that's useful. And I'm going to say that this was started from rest. So the maximum work is this. So when I look at that, I could then say that this is roughly going to be 1/2. The mass of the iron atom, we said, was 10 to the minus 25. And then the speed is 500 meters. So if you compute that number, it turns out to be about 10 to the minus 20 joules for the kinetic energy of an iron atom. As we said before, why should we care, right? This is tiny. By macroscopic scales, this is a tiny number. However, if I look at the change in the microkinetic energy, then this is the number of iron atoms times the kinetic energy of an iron atom And so when I look at this, this is 10 to the 25 times 10 to the minus 20 minus 0, and that gives me approximately 100 times 10 to the 3 joules. And this is our microkinetic energy. Excuse me. This is extremely large. And to get a sense of what do I mean by this, I'm going to look at the ratio. So to compare these, I compute the ratio of Kmicro to Kmacro. And what we're seeing here is that this is 100 times 10 to the 3 joules, and this guy's about 100 joules. So you could see that this number is 1,000 times larger. In other words, there is 1,000 times more Kmicro inside the iron block than its macrokinetic energy. So even though these micro energies are hidden. What do I mean hidden? They're hidden from our macro perspective. These are quite real. That's why we look at the micro energies. We can't ignore them. So when I look at the first law, you're going to see here is that there are two approaches to the first law. And you should be aware of them. There's this guy. This is the change in internal energy. And this is heat plus work. And I would say that this is a modern approach that focuses on the gas. What we're going to see here is that this approach is more physical. It's clearly more physical, but there's a cost. And the cost is we have to redefine thermal work. It's not the standard work. If you use the standard work from mechanics, then the first law reads differently. There's Q and there's W, but what happens now is that there's a minus sign. And what I would say here is that this approach is an old-fashioned that uses the standard work definition, like from mechanics. And we'll talk about this here in the next chapter here, but I would say that this guy turns out to be less physical. And really, what happens here is that in this old fashioned, what they do here is that they focus on the piston head, not the gas. Clearly, from chapter 1, I'm using the modern approach. And so that tells us here that when I look at the internal energy, I am going to have the plus sign here because I want to focus on the gas. So now what I want to do here is I need to make a real strong statement here, okay? And I would say that this is important. A measure of the internal energy tells us that the system has changed. So in other words, that if I look at this from a systemic viewpoint, we really have two states. In state 1, we're going to have some internal energy, which I'll call internal energy 1. And then what's going to happen here is that I'm going to be doing some working and I'm going to be doing some heating. And as a consequence, this internal energy will change. To measure the change in internal energy, and of course, I'm really talking about this guy, that this guy cannot be zero. There is a temperature change. In other words, the change in internal energy, in this case, it's of an ideal gas, will then tell us about the change in the microkinetic energies, and this is proportional to the change in temperature. So the important point is this statement right here. The temperature difference tells us about the change in internal energy. So what we're seeing here is that we measure changes in temperature to tell us if there's a change in state. So what the workings and heatings do is act as catalysts of energy change. So if I do working and heating and there's a temperature change, then I know that I've changed the internal energy. In other words, when I look at the work plus the heat being the change in internal energy, I'm saying that as I change the internal energy, I have catalysts of change. It's these guys that change the internal energy. It's these guys right here that are the catalysts that force changes in the system. But we don't use the first law, up to this point. Up to now, we've not calculated any energies. We've used the framework of the first law, because if you look at above, right, we're really talking about what? That we start at some state one, and we have our state variables. And then we then have our state two, where these state variables, at least one of them has changed. And it's this working and heating that caused the change in the state variables. So where do we go now? We now focus on calculating work, which is what I call a mechanical. Actually, I shouldn't say mechanical. I should say that it's a thermal mechanical that's not right. Interaction, in other words, working, and a heat interaction. Which is what I call heating. And what this is going to tell us is how do we change internal energy?